Life hacks are simple tricks that make our life easier, more convenient, or more beautiful. What all life hacks I'm showing you here have in common is that they use things for something other than what they were designed for. But why am I showing you these simple tricks today? Well, because in our work, we did exactly the same. We used the device for something other than what it was designed for. And this device I'm talking about is an inertial measurement unit, which you can see here in the image on the left. Inertial measurement units were initially designed for navigation purposes in aircraft and spacecraft and helped Apollo 11 and Neil Armstrong to get to the moon. Miniature versions of these IMUs, so-called microelectromechanical systems, were later designed for motion analysis in sports and for orientation detection in smartphones. And today I'm going to show you how we gave these small devices a new purpose, namely motion estimation in weight-bearing cone beam CT of the knee. With this imaging technique, as you can see in the video, we want to visualize the structures of the knee joint in a natural standing position, and by this analyze how the mechanical properties change under load. The problem with this imaging technique is that when you're standing, you're always slightly swaying, and this sway will cause motion artifacts in the resultant reconstructions. So the reconstructions that should look like this, so with very nice structures and clear borders, will look like this. So you can't really recognize anything there anymore. There's a lot of blurring and streaking. So the research question I want to answer today is, can inertial measurements be used for motion compensation in weight-bearing cone beam CT of the knee? To investigate the feasibility of this approach, we performed a simulation study using real recorded 3D motion. Of course, we are not the first ones that dealt with motion compensation in CBCT, and there exist some image-based methods, for example, anatomical landmark detection as proposed by Beer and colleagues, or a penalized image sharpness criterion. A second category of methods to approach this are external hardware-based methods. For example, Beer and colleagues proposed to use range cameras for surface detection, and Choi and colleagues put small metallic markers onto the legs of the subjects and tracked the motion of these markers in the projection images. Our proposed approach of attaching IMUs to the legs of the subjects falls into the second category. This pipeline will now lead through my talk, and we will go through it step by step. First of all, I told you that we're doing a simulation study using real recorded motion. So first, let's have a look at the motion capturing. For this, we used an optical motion capturing system, which can track small reflective markers that are placed on the subject's knees or on the leg of the subject. And we placed 7 such markers on the lower body of 7 healthy subjects and asked them to stand at a squat of 30 degrees and 60 degrees flexion for some time and recorded them. So now we know the motion of the markers, but we have no reference as to how the body actually moved. And for this, we applied then a biomechanical model, scaled it to the subject's height, and computed the inverse kinematics. This computation will basically give us the motion of the biomechanical model that best fits the motion of the markers that we placed on it. And these positions and trajectories of the joints of the model will be used as input for all our further investigations. With the motion of the biomechanical model, we did 2 things. First of all, we simulated motion corrupted CT scan, because of course we need a motion corrupted CT scan that we can later on correct. For this purpose, we used the XCAT phantom, which is a numerical phantom of the body, and you can see a slice through the knee here in this image. The nice thing about the XCAT phantom is that all the structures, or the shapes of the structures in the model are controlled by a set of points. So by deforming these points, we can non-rigidly deform the model such that it takes the pose of our biomechanical model. And we did this over time for the course of a scan, and then created forward projections of the model. And by this, we obtained the motion corrupted projection images. The second thing we did with the biomechanical model is we simulated IMU measurements. For this, please note the difference between the global coordinate system here, the fixed global coordinate system at the bottom, and the moving coordinate system of the knee joint, and the coordinate system of the sensor, which is shown here as a green box. The gyroscope in the IMU measures the angular velocity, so the rotation change over time. Since the sensor is aligned with the shank segment, we can use the orientation of the knee joint in the rotation matrix R and its first time derivative to compute the angular velocity. The accelerometer, the second component of the IMU, measures the acceleration. And for this, we have to take into account also the position of the sensor on the segment, so Psen, and the position of the knee joint, so Rsec, that change over time. And then we compute the second derivative. Note that here in this equation, there's also a vector g, and g is the gravity vector, because the accelerometer at each point in time also measures the gravitational force of the Earth. So now we're done with our simulations. Let's have a look at how we use the IMU data to correct the motion corrupted CT scan. So we start with the angular velocity omega and the acceleration a. But what we want to do is we want to revert the motion that happened during the scan in a global scale. What we want to do for this is we want to correct the projection matrices that are used for the reconstruction, and we want to correct them by multiplying affine motion matrix to it. And basically, we have to estimate these motion matrices. If we say that the initial pose is our reference pose, so the first frame, basically, we can use the identity matrix as our first motion matrix M0, and then update step by step by applying the global motion delta G. So we don't estimate the absolute motion anymore, but the motion change. But what is this delta G now? Well, if we have a look at our sensor, at each point in time, the sensor has a certain pose. So it has a certain position, so the lowercase vector r, and a certain orientation stored in the rotation matrix capital R. If the sensor now moves over time, then it rotates and translates. And this is basically exactly the global motion that we are looking for. And we can use it to update the pose step by step by step. But still, this is a global motion. And from our sensor measurements, they are only measured locally. So what we can do with them is we can estimate the local motion. So delta L, the motion change of the sensor. And this is again an affine matrix, which contains a rotation matrix, the orientation change G, which can simply be obtained by rewriting the angular velocity into a rotation matrix. So that was very simple. For the translation change, so for the position change or velocity, we have to integrate the acceleration. But we have to do this considering, again, the orientation change G of the vector over time. Additionally, you can see here now a vector G of t. This is, again, the gravity vector that we, of course, need to remove before integrating. And we need to do this considering, again, the orientation of the sensor, because depending on the orientation, the sensor measures the gravity. And the orientation can, again, be updated with our orientation change G. So now we have our local motion, and we can now transform this to the global frame by applying the sensor pose S, which we can then again update using the global motion. And by this, we close the loop. We start with our sensor measurements, and then we end up with the corrected projection matrices. Let's have a look at the results that we obtain. On the left, you can see a reference scan where no motion was applied to the XCAT phantom, and the reference pose, so the first pose was kept static throughout the scan. And you can very well see all the structures. You can see the bones that are drawn in white, and we see a lot of very nice borders. In the uncorrected case, as in the real image that I showed in the beginning, we have a lot of blurring and streaking artifacts, which can be corrected by an IMU-based method to a high degree. So the streaking and blurring is reduced. We also compared a method to a state-of-the-art marker-based approach that I showed in the beginning. And you can see that visually the results look very similar. Quantitatively, we evaluated the structural similarity index measure, which is 1 for identical images and 0 if there's no similarity. For the uncorrected case, there's a very low SM with 0.88 and 0.82 is achieved for the 30 degrees and 60 degrees squat. This can be improved to 0.99 and 0.98 with our proposed method, which is comparable to what the marker-based reference approach achieves. So to discuss this quickly, so I showed you that in theory, this works very nicely. So we can answer our question, can inertial measurements be used for motion compensation with a definite yes, but there's a but, because this was an optimal simulation that I showed you, but there are some things that we need to tackle in order to bring this to a real application. First of all, you saw that in the method that I described, we assumed the initial pose and velocity of the sensor to be known, which they are, of course, not. So we need to find an approach for initialization to estimate these parameters. Second, currently we are only estimating rigid motion matrices. But the motion might be non-rigid when, for example, when the angle between the knees changes. What we could do is we could take a second sensor and place it onto the thigh of the subject. And by this, we have more information about the motion of the thigh and the shank independently, and can use this for non-rigid motion estimation. And the last and probably most important point is everything happened under optimal conditions, but in reality, IMUs have a lot of error sources, for example, noise or drift or bias. And this might ruin our whole method. So what we need to do is also have a look at how will noise or other error sources influence our results. Good thing is that we tackled these three problems that I just mentioned in a follow-up publication that we already uploaded on arXiv, and which is currently also under review with a journal. If you want to know more about this, please read the paper, or you can, of course, also ask me in the discussion session. And with this, I'd like to thank you for your attention.